instructions on this first one are just to find the equilibria, right? I didn't ask us to do anything else. Though if you want, we can go through classifying the equilibria also. Which that's the primary thing you're being asked to do on the wet work, is to find and classify the equilibria. Do not ignore the additional instructions on there that are telling you to practice sketching the phase plane or the phase portrait. Because I guarantee you will have to do it on the exam on Friday. There's no way you're getting away with not graphing on the exam. So don't ignore that practice. But in terms of finding the equilibria, I'm always starting in the same place, whether we're talking about a single autonomous differential equation or a system of differential equations. Those equilibria are happening when my derivatives are equal to 0. By the way, the equations that I get out of this are the nonlinears. So if I look at that top one and I think about that rearranged as the equation y equals x, that's an x nonlinear. If I look at my second equation, I can factor an x out. And this is giving me the two y nonlinears, that x is 0 or that y is equal to 2. So these are my y nonlinears. Now the places where an x nonlinear and a y nonlinear intersect, that's where my equilibria are. So I can do that graphically, or I can just think about pairing the pieces up together. So I need something from here to be true and also for this to be true. So if x is 0, but x is equal to y, then 0, 0 is an equilibrium. Yes. The Jacobian, I like to think about this as calling my first equation f and my second equation g, mostly because I'm trying to avoid subscripts. Our textbook puts subscripts to that and calls it f1, f2. So my Jacobi matrix comes from doing a bunch of partial derivatives. So my first entry here, I'm looking for the partial derivative of f with respect to x. So my partial of f with respect to x is 1. My partial of f with respect to y is -1. When I look at my partial derivatives of g, my partial derivative of g with respect to x is what? And my partial derivative of g with respect to y is just -x. So that's generically my linearized form. So when I go to analyze stability, this matrix is going to be a little bit different at each equilibrium. When you have a linear system, the entries in this matrix will all be numbers, because all of my partial derivatives will just be numbers if it's linear. But for a nonlinear system, what this matrix looks like is going to depend on which equilibrium I'm at. So at 0, 0, our Jacobi matrix becomes 1, -1, 2, 0. And at 2, 2, our Jacobi matrix becomes 1, -1, 0, -2. As I'm plugging the x and y values into that matrix. Let's do the easy one first. What are the eigenvalues for this matrix? So what kind of point is it? Or rather, what's their, Drawing is not going to be an easy way to figure out if it's stable or unstable. I really need to know the stability before I try to draw it. What drawing it is going to show me is the direction that it's spiraling, whether it's spiraling clockwise or counterclockwise. But the eigenvalues are what's going to tell me whether it's stable or not. So let's go ahead and find those eigenvalues for the 0, 0 Jacobian. So at 0, 0, I'm looking for the determinant of 1 minus lambda, -1, 2, and 0 minus lambda, or just negative lambda. So 1 minus lambda times negative lambda minus 2 times -1. So that's a positive lambda squared, but a negative lambda and a positive 2. So that doesn't factor. If the 2 had been negative, we'd be in good shape. But since it doesn't factor, I'm going to use quadratic formula. So my lambda is going to be, that'll be 1 plus or minus the square root of -1 squared minus 4 times 1 times 2, all over 2 times 1. So 1 plus or minus, inside here, that looks like a -7. Square root of -7 all over 2. So if I rewrite this in its complex form, that's 1/2 plus or minus √7 over 2i. This is what tells me it's a spiral, because I've got that square root of a negative, and this is what tells me that it's unstable. So the real part of our complex eigenvalue is positive. So this one kind of follows the same rules as if it's not complex. So if this part's positive, I know we're unstable. If this part's negative, I know we're stable. Now, because we didn't do trig in here, we are not really gonna explore why that's happening with Euler's method, but it's Euler's equation that is causing this part to determine whether my oscillations are getting smaller in amplitude or bigger in amplitude. So that's really all you need to know, is that if this is positive, it means my oscillations in the spiral are getting bigger. And if this part's negative, it means my oscillations in the spiral are getting smaller. That first step is figuring out what are the equations for the null lines. So so this one factors, I can pull out a y, and then I've got 3 minus x, which means that my two equations for the null lines are y equals 0 or x equals 3. And these are my x null lines. And the reason they're x null lines is because they're coming from the dx dt equation. This one, if I set equal to 0 and factor in x out, I'm getting that x equals 0 or x equals 1. So these are my y null lines. And it's only an equilibrium if it's where, based on my colors, a purple line would intersect a red line. So what I usually do is just pick one of the two sets of null lines and pair them up with the other pieces. So if y is 0, then x could be 0. So that's the point 0, 0. If y is 0, then x could be 1. That's the point 1, 0. But if x is 3, it can't simultaneously be 0, and it can't simultaneously be 1. So the only equilibria here are 0, 0, and 1, 0. And if I were to graph those null lines, I'm not going to do the phase plane analysis, but if I were to quickly sketch those null lines, then my x null lines are happening at y equals 0. Sorry, I'm just gonna get my axes on here in a different color. I don't know if you can tell it's a different color. It is. At y equals 0 and x equals 3. And then my y null-clines are happening at x equals 0 and at x equals 1. So the only two places where I have a purple null-cline intersecting a red one are right here and right here at 0, 0 and 1, 0. So those are my equilibrium. Next up, if I'm going to classify, I need to find the Jacobian. So for me, just to keep track of it all, I like to label the outside of my matrix. So I know I'm doing F in the top row, G in the bottom row. My partials with respect to X in the first column, and my partials with respect to Y in the second column. So my overall Jacobi matrix, if I take the partial of F with respect to X, I'm looking at negative Y. If I take the partial of F with respect to Y, I get 3 minus X. My partial of G with respect to X is 2X minus 1. And my partial of G with respect to Y is 0 because it's 0. Good times. So my Jacobi matrix at 0, 0.
Why do you do like at 0, 0? Why don't you?
So when we're trying to classify the behavior very near the equilibria. So what we're doing in finding this matrix is we're linearizing the system very near the equilibrium. Now, actually, at the equilibrium, this matrix of partial derivatives is telling us exactly what that behavior looks like. So the behavior at 0, 0 might not be the same as the behavior at 1, 0. Just like in the previous problem, we had a saddle point near 2, 2, but we ended up with an unstable spiral near 0, 0. So each potential equilibrium is going to have a different behavior around it. I don't know if that answered your question. Maybe, kind of. So at 0, 0, my matrix of partial derivatives, which is how we're linearizing the system, becomes 0, 3, negative 1, 0. And my Jacobi matrix at 1, 0 looks like 0, 2, 1, 0. So that suggests to me that this one is a saddle. And this one we can call a neutral spiral or a center if there's no real part right here. Because I made a typo. So I'm going to fix my typo or roll with it as I wrote it. Roll with it? Okay. We'll roll with it as I wrote it. And I will fix my typo on the worksheet so that it's not still sitting there as a typo the next time I do this. Cool. Okay. But for today, there is a typo. And so if I set this equal to 0, then my null-Klein equations look like x equals 0, or I'm just going to rearrange this, y equals 5 minus x. If I set this one equal to 0, then I've got x is equal to 0, or if I rearrange this, y is equal to 7 minus 3x. So the interesting thing here is that because of my typo, the entire y-axis is in equilibrium. Because if x is equal to 0, it satisfies both differential equations. So this one actually has an infinite number of equilibria, because when x is equal to 0, both things are satisfied. So it's definitely not what I meant to write. So I'm now going to fix it to what I meant to write, which was to make this a 3y. Now life's going to be more interesting. And now these are my 4 pieces. So if I think about pairing these up, which you could also think about as sort of plugging things into each other, right? But if I start with x equals 0, and I pair that up with y equals 0, then that gives me the equilibrium 0, 0. If I pair up x equals 0 with this null sign over here, that's equivalent to saying I could plug in 0 to this equation, and I'm going to get y is equal to 7. So that gives me the point 0, 7. Next up, I'm going to take this equation. And if I pair this up with the y equals 0, that's equivalent to plugging in 0 for y. And if I do that, then I'm going to get that x is equal to 5. So that's going to give me the point 5, 0. 1, 2, 3 equilibria. By the way, each of those equilibria live on one of my axes, because all of those have either an x equals 0 or a y equal to 0. If we were talking in a biological context, that means one of our 2 species has died out. So, like, in terms of the textbook we're living in, that is for applications in biology, these are sort of 3 sad endings. This is the most sad. Everybody died. All of the critters died out. And then these 2 represent some sort of interspecies competition where one of those species has taken over the other one. Okay, which means let's find the equilibrium where both species are still in existence, meaning my last set of things to pair up are these 2 lines. How you want to solve that system of equations, we can graph them, we can plug one into the other, we can write a matrix and row reduce it. Let's not do that. So I'm going to opt for, since they're both already solved for y equals, I'm just going to set them equal to each other. So if 5 minus x is equal to 7 minus 3x, then 2x is equal to 2 and x is equal to 1. How'd I do? Okay. And if x is equal to 1, then y must be equal to 4. So I've got the point 1, 4. Let's just figure out what the Jacobi matrix looks like at 1, 4. So with respect to x, I might need to give myself a little bit more space in my matrix. My partial of f with respect to x, make sure I get this right. I've got 10 minus 4x minus 2y. My partial with respect to y, I've got negative 2x. For my g equation, my partial with respect to x, I've got negative 9y. And my partial with respect to y, I get 21 minus 6y minus 9x. How'd I do? So at 1, 4, this is gonna get messy, but it's okay. So if x equals 1 and y equals 4, then I've got 10 minus 4, so I'm at 6, minus 8, so -2. And another -2. And if y is 4, that's -36. Now I've got 21 minus 24, so that's -3, minus 9, so -12. And if I classify that by, I really don't have space on here, so I'm gonna have to flip the page. Does anyone need me to pause on flipping the page? Okay, I'm gonna pause for a second. Pause. I'm looking for the determinant of -2 minus lambda, -2, -36, -12 minus lambda. I know it's a little bit gross, but I have left one that's on here a little bit gross just because we all know that sometimes the web work problems are a little bit gross. So I'm not afraid to use a calculator if we need to. So that's gonna be -2 times 36, so 72. And over here, when I distribute out, I'm gonna have lambda squared. That's a +12 lambda, a +2 lambda, so plus 14 lambda, plus 24. Who knows? Maybe it'll factor. Lambda squared plus 14 lambda minus,
What is it?
I don't know.
Negative.
We good? Okay. And 38. $38 is 2 times 19. I'm not gonna get a 14 out of that. We don't have any other options. So it's going to be quadratic. And I'm gonna have lambda is equal to -14 plus or minus the square root of 14 squared minus 4 times 1 times -38 all over 2 times 1. Well, I know it's not a spiral, because whatever is inside of that square root is going to work out to be positive. I know it's going to be a saddle, because without actually working the numbers inside of the square root, whatever this is bigger than 14. So my positive swing is going to get me positive, and my negative swing is going to stay negative. So I know that this is a saddle. Null signs, right? We're just going to draw all the null signs first, because I think that's going to help here. And if it doesn't help, it's okay, because this stuff is hard. And we just need practice. Okay, so I'm going to start by drawing all my null signs. So y equals x, that's my null line. that is a dx dt equals 0 nullcline. So everywhere on this nullcline, I know my arrows are pointing straight up and down. Now I'm going to get my other nullclines. So my dy dt nullclines are x equals 0, which is secretly the y-axis, and y equals 2. So this is a dy dt equals 0 nullcline. This is a dy dt equals 0 nullcline. Everywhere along my dy dt equals 0 nullclines, I know that my arrows should point left, right. They should have no up, down to them because the y part is not changing. I don't really know how to draw the left rights on the one that are already horizontal. I'll just give myself some placeholders in there. So my equilibria are happening when a dy dt nullcline crosses a dx dt nullcline. So I can see them on here. That's our 2, 2, and that's our 0, 0. I'm going to use a lot of paper on this one. So I'm going to leave this sitting here for a second. Oh no, I'll just do it tiny over here. I can do it tiny. So I'm going to leave this sitting here for a second. And now I'm just going to think about our dx dt nullcline of dy dt, or sorry, of x equals y. And let's pick a point on either side of that to see if I point left or right. So I'm going to pick a point down. It doesn't really matter. I'll pick a point right here. Like if I pick the point 1, 0, I want to know, is my dx dt greater than 0 or less than 0 at the point 1, 0? Greater? And then my dx dt over here is going to be less than 0 because I've crossed a nullcline.
And you plug it into the x and not the right.
Correct. So if we do these as separate, and I figure out my left rights, and then I figure out my up downs, and then I stack them on top of each other, that's kind of what you've been seeing in lecture, right? It's not the way I approach it. I'm just trying to be consistent with what you, so everywhere over here, if dx dt is positive, all of these arrows should be pointing to the right. All of them on that entire side of the nullcline. Because the nullcline is like a dividing line that is in a particular direction. So everywhere on the other side of this nullcline, my arrows have to be pointed to the left.
Points 1, 0,
I plugged that point into dx dt to figure out if I'm pointing left or right.
What happens if you plug into dy dt or what?
I don't even know, like, it's not at all wrong, actually. It's really genuinely not at all wrong.
The dividing line.
But the dividing line is dx dt, right? And so the truth is, if I had all the time in the world, or if I was using R, I would just plot arrows everywhere. This is just sort of one tool that we have to try to get the information on our graph faster. And different people have different approaches to it. Whether you want to look at what the vectors are doing on the nullclines, or look at what the vectors are doing off the null lines. So I'm going to take all of those left, right vectors, and I'm going to say everywhere out here below my purple line, I'm just going to draw myself some vectors that are pointed to the right, everywhere below that line. And everywhere on the other side of the line, I'm going to draw myself vectors that are pointed to the left. By the way, that means that I know what direction the vectors point along these dy dt null lines. And now I can do my analysis of the dy dt null lines. So my dy dt null lines, I think I'm going to squeeze them in down here. Let's see how that goes. So for my dy dt null lines, I know that I've got the x equals 0 and the y equals 2. Which has essentially divided this into 4 quadrants. So in each of those 4 quadrants, I'm looking for what the sign of my dy dt is. Is it greater than 0 or less than 0? So I'm going to pick something in this quadrant down here, and I'm going to just choose the same point, 1, 0. And this time I'm going to plug it into dy dt. So if I plug in 1, 0 here, I'm greater than 0. So everywhere in this little quadrant, I know I'm pointing up. And every time I pass a null line, I'm going to switch direction. So I was pointing up here, so I'm going to be pointing down in here. You could also pick a test point up here, right? Like I could pick the point 1, 3 and plug it into dy dt. And if I pick the point 1, 3, you'll see that this is less than 0. So all of these arrows should point down. Over here, I've crossed another null line. So those arrows should point up. And down here, I would cross another null line and those arrows would point down again. So if I layer those arrows onto my big picture, then everywhere in this quadrant that's marked out, my arrows have to be pointed down. Everywhere in this quadrant that's marked out, and let me go ahead and put one down here. Everywhere in this quadrant, I know my arrows have to be pointed up. Everywhere in this quadrant, they're pointed down. And everywhere in this quadrant, they're pointed up. And now I can fill in the direction of my arrows along the dx dt null line. So these are all going to point down. I've crossed a null line. These are going to point up. Crossing another null line, those are going to point down. So in the places that are not actually on a null line, I have to think about combining those vector directions together. So out here, I'm going to be pointed up and to the right, 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 down and to the right, down and to the left, down and to the left, down and to the left, down to the left, down and to the left, up and to the left, up and to the left, down and to the right. And the only place that I didn't do a good job of picking an arrow in here, but I know that in here, my dx dt is pushing me to the left, and my dy dt is pushing me up, which should mean that I was going up and to the left over here. Here's my cleaner version of it. So that's a dx dt is equal to 0. And here are my dy dt's equal to 0. So if I look at the dx dt is equal to 0 null cline, and we figured out that out here dx dt was greater than 0, and over here dy dt, sorry, dx dt is less than 0. I'm going to transfer this information onto the null clines over here. And the way that I'm going to do that is any part of my dy dt null clines that are on this side of that y equals x line, this says my arrows have to point to the right. So on this side of my picture, all of my arrows have to point to the right. So on this null cline, I have to be pointed to the right, and on this null cline, I have to be pointed to the right. On the other side, I have to be pointed to the left. So if I flip this over and I block the other side, then on my red null clines over here, I have to be pointed to the left. And then I can do the same for the other ones. So now I draw in the dy dt null clines. This one I've got 4, it kind of breaks things up into 4 quadrants. So we already did the mathy part, but our dy dt up there was negative. So that means my dy dt down here is positive, cross another null cline, dy dt is negative, cross another null cline, dy dt is positive. So now in terms of my picture, if I go to figure out my arrow directions on my purple null clines, I just kind of have to look in each quadrant. So if I look in that quadrant, then along that purple null cline, that arrow has to be pointed up. If I look along that quadrant, in that, my null cline's got to be pointed down. If I don't have a purple line up here, so I don't have to worry about it. So here, my purple line is going to be pointed down because my dy dt. And for me, I can already see that this is a saddle because I have one, in one direction, my arrows are kind of coming together, and in the other direction, my arrows are headed apart. So I can see that 2, 2 is a saddle, and over here, I can see the spiraling happening, right? The catch is that for that spiral, it's not I can't tell if it's a stable spiral or an unstable spiral, right? We had to do the Jacobian to know that that was an unstable spiral over there. Gonna kind of stack the things on top of each other. So now if I want to know what's happening out here, I know I'm below the purple line, so I point to the right. And I'm in this quadrant, so, and I probably would do this up, down, up, down. So if I'm at a point over here, I point to the right and up. So everywhere in here, I'm pointing up and to the right. If I'm in here, I point to the right, but now I'm pointing down. So over here, I'm down and to the right. If I'm in here, I'm below the purple line, so I point to the right, but I'm in this chunk, so I point down, so I'm down and to the right over here. I think I end up personally with a less messy picture if I start by doing the null lines and drawing the arrows along the null lines. In here, I'm above the purple line, so I'm pointing to the left, but I'm in this upper quadrant, so I'm down and to the left. Over here, I'm in this quadrant, so I'm up and to the left. Here, still pointing to the left because I'm still on that side of the null line, but now I'm pointing down. So I'm down and to the left. So if I had an initial condition, then we can sort of sketch what that possible trajectory looks like. So if I had an initial condition, let's say I started here, then I'm getting pushed up and to the right. Let me start closer to this guy. So I'm getting pushed up and to the right. But when I'm still getting pushed kind of up and to the right. So one of two things is going to happen, right? I'm either going to end up doing this or I'm going to end up doing this. So the behavior near that other equilibrium, right? I'm going to start looking like a saddle. The behavior over here, if I kind of work backwards in time, this was a spiral. So I'm spiraling out and heading over there. Why is it a spiral?
Is it spiral?
Because we did the math.
Wait, no, isn't it spiral because of the spiral if it has a knife?
Yeah.
Wait, oh yeah, never mind.
I was like, which we did at 0, 0. Yeah. Yeah, we did have a complex solution at 0, 0.
What is spiral just going in a circle? Yeah.
So a circle. Oh, was this a center? I thought it was an unstable spiral. Uh-huh.
Yeah, it's unstable.
So if it's unstable, that means that kind of my amplitude of the spiral is growing. If the real part is 0, that's when I have a center and it's going to look like an ellipse. It's not necessarily a circle, but it's going to look like an ellipse. Yeah.